All right, so I should say that once again, the lecture notes have been updated to cover through the end of today's lecture. The section 4 is longer than I will probably get through today, so wherever I stop today, I'll pick up on Friday. So the plan for today is to talk about these objects that have been mentioned on several occasions so far, but haven't been defined yet, Farb-Fontaine curves. These are a really beautiful class of objects that sort of came into existence at around the same time as the theory of perfectoid spaces was coming together. The Farb-Fontaine curves are basically meant to be, so these are, as I alluded to on Tuesday, these are like moduli spaces of untilts. So let me put that in context. So throughout this lecture, I'm going to fix F, which will be a perfectoid field of characteristic P. So the Farb-Fontaine curve associated to F is going to be an object that somehow parameterizes the untiltings of F. Well, in order to motivate the definition, let me make a comment about untiltings of F. So reminder, so isomorphism classes of perfectoid fields K, which tilt to F. So if you want to specify a perfectoid field together with an isomorphism of its tilt with F, these correspond. This was the goal. The goal of the first two lectures was to establish this correspondence. These correspond to the primitive ideals of the ring A-inf of F, which I'll remind you just this once, is the ring of Witt vectors of the valuation ring of F. This one? Reminder. So this was something that we learned in the first two lectures, is that the isomorphism classes of perfectoid fields that tilt to F, where by isomorphism I mean if you have two of these things, then an isomorphism between them should commute with these isomorphisms. So isomorphism classes of perfectoid fields with the tilt F are in one-to-one correspondence with primitive ideals of the ring A-inf of F. And remember, a primitive ideal meant that it was a principal ideal, and the generator had this special property about its first two Witt components. Well, that's almost true. I mean, it is the case that primitive ideals give rise to isomorphism classes. There is, however, something missing in this, which is that the class of primitive ideals is acted upon by Frobenius. And if you have So if I take a primitive ideal I, then its image under Frobenius is again a primitive ideal. But of course, perfectoid field K, the thing upstairs, does not have an action of Frobenius. So the role of Frobenius here is that Frobenius defines an isomorphism of this untilt with this untilt. So really, you shouldn't be thinking of primitive ideals. You should be thinking of the set of primitive ideals modulo the action of Frobenius on that set. That's what really corresponds to these things. Because this isomorphism does not correspond to anything meaningful on this side. You should kind of divide it out when you make this correspondence. So the construction of the Farb-Fontaine curve that I'm going to give you starts with this point of view that untilting corresponds to looking at primitive ideals, which sort of give rise to points in some space associated to this thing, but you should really only consider those points modulo the action of Frobenius on the space. So, okay. So with that in mind, let me start making some spaces. So I'm going to define a space called y sub f first. This is not the Fontaine curve, but it's going to be related to it. So what am I going to do? So remember, maybe I'll just write ANF instead of ANF of f, because f is going to be fixed. So in the notes I was consistent about putting the f in, but maybe for the board I'll just omit it. So we've talked about adic spaces in the afternoon lectures. So if I tell you how to give ANF a topology, I can make this adic space. So I'm going to put the p comma bracket var pi adic topology, where var pi is a pseudo-uniformizer. It doesn't matter which one you pick. I just need some way to make an ideal that's concentrated at whose radical is the maximal ideal, but it's finally generated. Okay, so ANF is complete for this. So ANF is a Huber ring for this topology. It's not Tate, because the only units are things of trivial valuation. So this is not an analytic adic space. So I could make it analytic by taking out the one point that corresponds to where these things both vanish. But I'm going to do slightly more than that because I want to do this division. I'm going to take out the entire zero locus of p times var pi. So in the picture where you think of this as a two-dimensional local ring, if you imagine the spectrum of a two-dimensional local ring as kind of something like this, where over here you have something corresponding to p equals 0, so over here I have something corresponding to var pi equals 0. I'm sort of I'm excising both of these bits here, and I'm getting something in here which is not going, so this is going to be not quasi-compact. But the action, and the reason I took these sort of axes out is the action of phi on here is, on YF, is properly discontinuous. Meaning that I can cover this thing with, every point has a neighborhood which is disjoint from all of its translates. Right? Like a properly discontinuous action means you have a point, every point has some neighborhood where the action of phi kind of moves these things to disjoint copies of each other. Right? And if the action is properly discontinuous, I'll show you why that is in a moment, but if the action is properly discontinuous, then I can make something which I'll call XF analytic. If the action is properly discontinuous, then I can take the quotient, and this will be an adic space. Well, I also have to justify that this thing, that the rings involved here are sheafy, but at least set theoretically, this is going to be a well-defined topological space as soon as I convince you of this. And this is the thing that's eventually going to be the adic Fontaine curve associated to F. Yes, so the plus in this case is ANF and itself. But ANF has a non-trivial topology, so this is not just the scheme. Okay, so why is this action properly discontinuous? Well, I can just give you some open sets that do this. So let me just write some down. So I'm going to give you two families. There's some flexibility in the definition here, but this is just the ones that I used. So one of these is that valuation of P is going to be between valuation of var pi to the p to the n and some slightly larger power. So the slightly larger power goes over here because everything is less than 1. So p to the n plus, I think I put here p to the n minus 1. The idea is that this is strictly between p to the n and p to the n plus 1, even if p equals 2. And then the other guy is going to be the same thing, except it's going to go from here to p to the n plus 1. And then over here, I want so if you imagine, if you imagine, think about rank 1 points, right? P has some value. P has some absolute value. Var pi has some absolute value. You're taking the log of one of those with respect to the other. It's going to be some number in the range from 0 to plus infinity. Var pi has the effect of shifting that by multiplying that by a factor of p. So I'm basically chopping the log space into sectors. So these things certainly cover the entire log space, and they translate. These things translate to each other. And I've made them disjoint, so because this thing is less than p to the n plus 1. So yeah, I've now got a covering by two families, where each family consists of a single, of the orbit of some aphanoid. These families, each orbit consists of a bunch of pairwise disjoint things, and this is a covering. So this witnesses the proper discontinuity of the action. Okay. Let me sort of pause here for a moment to make sure this sinks in, because this is important. Because I've sort of, this is going to become a little bit more clear later. This is more like a proj. Like when you take a two-dimensional, like this is a good example to try. Like if you actually were to take a two-dimensional local ring and do the analogous thing here, you would see a one-dimensional adic space, because somehow you, right? Like if you have if I actually started with something analytic here, like if I start with like an n-dimensional Tate algebra, then that's over some field with a rank 1 valuation. That's sort of an extra dimension that you don't see. But here you don't have that dimension, and right here you don't a priori have any norm on either of these things. So you kind of lose one dimension by normalizing one or the other of these by normalizing the absolute value of one factor or the other. Yeah, so it's like I started with a two-dimensional thing and I took out took out the close point. Now it's really only one-dimensional. So, yeah, that's okay. So now I at least understand what this set is, what this topological space is, but I haven't yet convinced you that this is a meaningful adic space, because I need to sort of look at what these rings are and see that these rings are reasonably behaved. In order to do that, let me give you another point of view on what those rings are. So these rings are naturally related to what are called Gauss norms on A-inf. So let rho be a number from the 0 to 1. I'll define the rho Gauss norm on ANF. So it's going to take non-negative real number values. So it's defined in the following way. So as usual, my candidate element of ANF can be written as a power series in P, whose coefficients are Teichmüllers of elements of F. And the rho Gauss norm of this is, well, right, the analogy here is that this is a power series in P with coefficients in F, all in air quotes. So what do I do here? So I'm going to fix let's fix an absolute value on F. You could also fix the p-adic absolute value and do this in the opposite order, but to make the analogy work better and to follow the notation in Farg-Fontaine, let me do it this way around. If you look at some of my old papers, I tend to do it the other way around, but let's do it this way around. So fix the absolute value on F, and now what I want to do is basically renormalize the p-adic value, p-adic absolute value, relative to the F absolute value, and this parameter is telling me how I'm doing that. So what I'm going to do is I'm going to declare this thing to have absolute value the max over n of, well, there's the absolute value of x n bar times rho to the power n. So I'm specifying that rho has absolute value, that p has absolute value rho, which had better be between 0 and 1, but I'm not modifying the absolute value on f. So as I vary rho, different terms contribute differently to here, and in particular, for a general sum, as you vary rho, different terms will contribute in different ranges. Different terms will dominate in different ranges. Right? This is just like taking Gauss norms on say a power series over ZP or something. And so then there's a couple of key lemmas that say this really does behave like a Gauss norm. One is that, well, the one that I want is that it's actually an absolute value. But before I say that, let me mention something which is easier to check, namely for fixed x, the function rho maps to x of rho, or x norm by rho, is continuous and log convex. So for example, if rho is the geometric mean of two other parameters, then the norm with respect to rho is bounded above by the geometric mean of those two norms. I claim the proof of this is basically trivial. Why is that true? Well, suppose you had a single term here, then this would certainly be true. Just because you would just be varying rho in here. And so this log convexity would be sort of trivially true if you had a single term, but because you're taking a union of you're taking a max, right, so maybe I should just write the inequality here. So if rho equals rho 1 to the t, rho 2 to the 1 minus t, then x rho is bounded above by x rho 1 to the t, x rho 2 to the 1 minus t. And t is in the range from 0 to 1 inclusive. Right, so this inequality is obvious if there's only a single term available, and otherwise, well, when you take the max of the things if you take the max of the contributions over here, that's certainly dominated by, well, you're getting the max of a product of two things. Well, the max of the product is less than equal to the product of the maxes. So this really is a really easy statement, but it has a fancy name. This is the analog. This is some sort of analog of the Hadamard three circles property in complex analysis. Right? In complex analysis, if you take a complex analytic function on some region and you take, say, a punctured disk or something, and then you take the maximum value on circles, then that has this log convex property with respect to the radius. So this is some much more mundane statement along those lines, But in fact, you could prove this by the same sort of argument. You write the thing as a Laurent series, and then each term of the Laurent series, the inequality is trivially an equality, and then you have to make sure that, well, okay, it's not quite that easy because you're not taking maxes, but it's not so far off from the actual proof. Okay, so that lemma is easy, and that lemma makes it possible to make this lemma, which otherwise, if I didn't do this first, I actually don't know how I would prove this. This would be kind of tricky. So the next lemma is that this thing actually this sub row actually is a multiplicative absolute value. Missing a letter here somehow. Okay, why is that true? So there's two steps. One is to prove the strong triangle inequality. I'll do that first. You might think, well, I should do multiplication first because the Teichmuller maps behaves better with respect to multiplication. But of course, if you multiply two things like this, you do a bunch of multiplication and then you have to do a bunch of addition afterwards to consolidate the terms together. So in fact, it's easier to do addition first. It's easier to understand addition in these coordinates first. So the strong triangle inequality. So right, the strong triangle inequality, there's something to prove because the effect of addition is not simply to add coordinates. The effect of addition is, right, if sum xn p to the n plus sum y bar n p to the n equals sum z bar n p to the n, then z bar n is equal to x bar n plus y bar n plus some correction term. What is this? But the point is that this correction term is, well, I don't need to know too much about it. I just need to know the following. So first of all, it involves things of index less than n. So I'm going to write this as if it were a polynomial. It's not literally a polynomial because it involves not powers of these things, but fractional powers of these things with p's in the denominator. But that's not a serious issue. So the point is that this is homogeneous of degree 1 with z coefficients. That's all I'm going to use about this thing. And so if you just stare at what the formulas are telling you, this is really all you need to know in order to check the strong triangle inequality. You sort of check term by term, you sort of check term by term that this thing is bounded by what it's supposed to be bounded by. And the point is that because this is homogeneous, it doesn't hurt you. So that's about all I want to really say about the addition. So as I said, it's better to do the addition first before doing the multiplication, but the multiplication is easy in a certain situation. So note, regarding the multiplicativity, so if each of x and y, so I'll call this one, so I'm trying to show that absolute value of x times y is equal to absolute of x times absolute of y, and x and y I'm going to write in terms of their coordinates. I won't write it out on the board again. But if each of x, y has a single, so what is clear? What is clear is that, so it's clear that you're getting something submultiplicative because, Yeah, well, how do you get this product? Well, you multiply a bunch of, you write each of x and y as a sum of monomials, you multiply each of those monomials together, and then you consolidate. So when you consolidate, we already know that you don't make anything bigger. And of course the products, the maximum, if you split up x and y and you form the individual products, at least one of those, the largest any of those products can be is, well, you take a dominant term from x and a dominant term from y. Where? So yes, I'm trying to show this. What is clear is that you have an upper bound. So the inequality this way is clear for the reasons that I'm just saying, that this thing comes from you take a dominant term here and a dominant term here, and that certainly bounds everything else that you produce when you make the product. So the hard part is to check that you actually get an equality. Well, thinking about I used the strong triangle inequality. So I'm using the strong triangle inequality here in this step. So when does the strong triangle inequality give you an equality? Well, when the two things are, when one of the terms is dominant and the other one isn't. So so this has equality when each of x and y has a unique dominant term. So if x and y each have a unique dominant term, then clearly only one product of terms contributes, because it strictly dominates all the other ones. When you add things up, that one persists. But of course, in general, if I take a general x, y, and rho, it is not the case that only one term will dominate. So here's the trick. You don't, right, you might be thinking of this as, well, I first fix rho and then I quantify over all x and y. But I mean, there are three for all quantifiers in that statement. So let me just switch the order. So let me first quantify over x and y and then vary rho. For given x and y, so here, that's the thing. If you vary x and y, then for most rho, x and y each have only one dominant term. So let me show you a picture of why this is. And the picture is a Newton polygon. Right, so you make so if I have an element x of a inf, how do I make the Newton polygon? Well, I plot points of the form n comma minus log of the absolute value of xn bar. And then I draw the lower convex hull of those points like I normally would. So this is going to be infinite in this direction. I suppose it's discrete in the horizontal direction, but since there are infinitely many values of n, potentially it goes out infinitely far. And so, right, what's going on here is something like the Legendre duality for convex functions. I plot these points, and then, right, I can read off these things. These things are telling me, like, if I find the support line of some slope, where does it intercept? Where does it have its y-intercept? Like this. And so as you vary the slope, right, for most values of the slope, the contact point is unique, and there's some discrete set of values where there are multiple contact points. So when I say most here, I mean away from a discrete set of values. So for given x and y, for most values of rho, it is clear that you have multiplicativity on the nose. And then, well, for the bad cases, you just use continuity. to fill those in. So that's how you know that you actually get a norm, multiplicative absolute value. So now I have all of these absolute values on A-inf. So now let me define a ring by modifying A-inf and then completing. So so take a closed interval inside 0, 1. I'm going to define the ring B sub I to be the completion of, well, A-inf, if I just took A-inf, well, okay, this is, I'm writing this in out of order, so there's something missing here, but so I'm going to define another norm, sub I, which is the sup over rho in I. But yes, go ahead. Yeah. So right, they occur right as you in terms of the geometric picture. Those discrete values occur when you actually get a segment of positive length, when the contact line actually doesn't just pass through a vertex. But those are discrete in the space of values of rho, and so for any given x and y, you know that right if you vary rho, then the norm of x varies continuously, and the norm of y varies continuously, and the norm of z varies continuously. Z being the product. So you can just fill in those missing values by continuity. So you get the equality on the nose for most values of rho, and then for the rest it follows by continuity. Why is this? I just define. I take the lower convex hull of the set of points. So right, it's the usual thing you do when you define a Newton polygon. You draw some points, and then you take the lower convex hull of those points. Right. So I'm plotting. This is the lower convex hull of the points that you put down. Okay, so I'm going to define another norm on A-inf by taking the supremum over all values in a closed interval, but I know I have this log convex property. So what does the log convex property tell me about this supremum? Well, where can this supremum be? Where can the maximum actually occur? Well, it can only occur at the endpoints. So this is the max. So if I write I as rho 1, rho 2, then this is the max of the two endpoints. So you don't really need to take a supremum. It's just the maximum of two multiplicative absolute values. So this is, of course, when you take the maximum of two multiplicative absolute values, you don't get a multiplicative absolute value. You get something which is well, it's submultiplicative still. It's also power multiplicative in that norm of x to the n is norm of x to the power n. Right? Because when you multiply the same thing with it, when you multiply two powers of x with each other, you get the max. Well, if you multiply x by itself, then you get the maximum either. The two factors, right? The issue with multiplicativity when you take this max is you have an x and a y. Well, one of them the max might occur on this side, one of them the max might occur on this side. But that's not a problem when you have the same factor or by induction powers of the same factor. Okay, so somehow right now what I've written on the board is not interesting, because if I were just complete A-inf is already complete with respect to this absolute value. So, but what I'm going to make this interesting by inverting the things that are supposed to be invertible in YF, namely P and Teichmuller of some pseudo-uniformizer. Inverse. So invert these things. A invert. So I'm going to take A inverse, adjoin this. So each of these norms extends by multiplicativity to this localization. It's algebraic localization. So I can still talk about this. And now I have something which is genuinely not yet complete, so I have to complete it. Right, right. So I'm inverting, I'm starting with something morally two-dimensional, and I'm inverting, and now I'm going to get something which is not just morally one-dimensional, it's actually literally one-dimensional. So proposition, this B sub I is not, it's in fact Noetherian, it's actually a principal ideal domain. So it's actually one-dimensional on the nose and more. So I don't want to say too much about the proof of this, but the key idea in the proof is, the idea of the proof is you use the fact that the associated graded ring, right? When you have a ring with a norm, you can define an associated graded ring. So it's a Laurent so the associated graded ring here is a Laurent polynomial ring in one variable over the graded ring of F. So this is a little strange because this is not an F algebra, right? It only has a multiplicative map from F, but it's still the case that the graded ring of this thing is an algebra over the graded ring of F, and the difference is that you have to sort of adjoin a generator corresponding to pi, to P, and then also its inverse. And so the associated graded ring of this thing is basically is a Laurent polynomial ring, so you have a notion of degree, which you can use to do a Euclidean division. So this ring admits a form of Euclidean division. It's actually a Euclidean domain for a certain degree function. Yes, so this is, I'm using heavily the fact that, yeah, I'm using information about the theta map and kind of the behavior of these Newton polygons and this kind of thing. So F also has an absolute value on it, so it also has a graded ring. No, but right, I mean, any ring with a norm, I can define a graded ring by taking, well, when I say graded ring, it's graded in positive real number degrees, rather not integer degrees. Yeah, so it's a graded ring in slightly generalized sense. I give a reference to it in the notes. It's actually a little bit. I mean, maybe a good place to read about this is Fargan-Fontaine do a version of this, which is a reasonable. It's a sort of niggly analytic proof, no matter how you do it. You can also I also have a paper about yes, I should state another result, and the reference for that maybe is also a good place to read about this. So. Yeah, but this is not particularly easy to prove even once you know the idea. It's kind of a fiddly analysis argument. Yeah, so this ring is Noetherian, but I can say more than that, and I need to say more if I want to use the criterion for sheafiness that we had earlier in the week. So BI is not only Noetherian, which follows from this, but it's strongly Noetherian. That is, if you take the Tate algebra in any number of variables over this ring, it's Noetherian for all n. So this is a similar argument to the proof of the PID, but now instead of doing Euclidean division, you use Grobner bases in a similar way. Which one is Noetherian? Oh, strong here. BI, the Tate algebra in n variables over bi is Noetherian. Sorry. If this ring is already, yeah, this ring I think is already a PID. In fact, even if you just invert this one, I think that's enough. It's not enough if you invert P, because then you can take like decreasing powers of this thing. But as soon as you invert this thing, then I think it's a PID already. But that doesn't formally imply this though. You still have to check something. So it's not an immediate consequence of the algebraic localization being a PID. Okay, so this, and I'll just mention in passing, these rings sort of look like affinoid algebras, and there's a lot one can do about trying to prove that they behave like affinoid algebras. So for example, one of my PhD students proved that this ring is, that these rings are excellent. Excellent, in the sense of, universally Japanese and blah, blah, blah. How do I prove that this is Noetherian? So as I said, you prove that this thing is a PID by exhibiting some sort of Euclidean division. Well, the higher dimensional analog of Euclidean division is the theory of Grosvenor bases. So you basically show that there's some sort of theory of Grosvenor bases for this ring. And that's how I prove the Noetherian property. Yeah, there's something like a Weierstrass preparation. Yeah, the short answer is yes. There's something like Weierstrass preparation going on. Yeah, and if you just go back to here, these rings have, in these rings you have factorization according to the Newton polygon and this kind of thing. So there's a lot of things that you might expect to be true from the pictures turn out to be true, but the proofs take some patience. Okay, so now, right, so the point is that, now what does this have to do with the Farg-Fontaine curve? Well, let me just align these things. If when rho 1 and rho 2 are rational powers, of the norm of R pi, then Bi is the structure presheaf evaluated on one of these open sets that I was considering. Not quite only the exponents differ, right? So you have a rational subspace that looks like V of bracket var pi to the S2 less than or equal to V of P less than or equal to V of bracket var pi to the power S1. And okay, these are not integers, but you can clear the denominator to make a valid equation. And yeah, so the spectra of these rings form a covering of YF. So YF is a Noetherian adic space, and it's analytic. Because I have these strongly Noetherian Huber rings, so they're sheafy, and I can put these together to make, and as is XFN, because it just inherits that property from the covering. Okay. Great. So now I have a really nice adic space. It basically is one-dimensional, so it looks like a curve. Of course, it's a slightly weird construction because this space, right? This lives over QP, but not over F in any meaningful sense. These rings are not F algebras. Right? Because they're in characteristic 0 and F is in characteristic P. So they're not F algebras, but nonetheless, this somehow sits over F. when I talk about, I'm planning to say something in the next lecture briefly about relative Farg-Fontaine curves, where instead of a perfectoid field, you take a perfectoid ring as the base, and this is going to be an even more strange situation. And here, because this thing sits over, it's not hard to imagine this space mapping to a point in some topological way. We're not really going to use that structure right now, but it will make a difference in the relative situation. Okay, so shoot, I don't know if I have the right, hold on. Yeah, these things form a covering of YF. Right, I took a special covering of this type earlier to show that it was properly discontinuous.
So when you say it's ellipse over QP, what do you mean?
I mean, it's a space over, all of the rings here are QP algebras. So in the world of adic spaces, it maps to, SPA, QP, ZP. Well, this is a Noetherian. This is a PID, so it's Noetherian of dimension 1. Yeah. Okay. Okay, now I have the right version of this. Okay, so now let me tell you about the schematic version of this story. So, in fact, this is not the order in which this theory was developed. When Farg and Fontaine originally did this construction, there was no theory of perfectoid spaces floating around. People hadn't really thought about adic spaces in this non-finite type adic spaces. So they directly constructed the schematic version of the Farg-Fontaine curve. But let me tell you how to think about it coming from the adic space version, which I think is, in hindsight, is more natural. So I'm going to define a line bundle, O of n, so n is an integer here. So I'm going to define the line bundle ON on XFN. Well, okay, so XFN is the quotient of YF by a free action of phi. So a line bundle on the quotient can be specified by giving an equivariant line bundle on the upstairs space. So this is going to be the phi equivariant line bundle on YF. Now here, I'm going to take a trivial line bundle, which is well, maybe to say it's trivial is a bit misleading because it's only trivial as an underlying line bundle. So it's free on one generator. Call it V, or maybe I shouldn't call it V because V looks like evaluation. What's a good name for a generator? E, I guess, I don't know. Satisfying the pullback, the action of phi on this thing multiplies that by p to the minus n. This minus, we'll see why this minus is there in a moment, maybe. Well, we'll see in the next line already. Oh, epsilon is E. Yeah, I need a good name for a generator. What do I call this generator? In my notes, it's boldface V. Because I think of it as a vector, but yeah, let's just call it E and hope that I can remember to write it correctly. It won't come up very often. Okay, so I have a line bundle on here. So now that I have a line bundle, I can try to define, I can do the following. I define a graded ring. So P sub f is going to be the graded ring. So this is in the usual sense of a grading. So this is graded by non-negative integers additively. And, well, what am I going to do? Well, you can sort of guess. I'm going to take the sections of O of n. What is this really? This is the sections, if I take sections of the structure sheaf on Y, these are the things that are fixed by phi minus p to the n. That's why I put the minus here to make this work. Yeah, so I'm defining a line bundle on XF and by specifying a phi equivariant line bundle on the cover by phi. I'm sorry? Yeah, so if you didn't keep track of phi, it would be trivial, but it has a non-trivial action of phi on it. Okay, so this a priori just, I mean, formally it's not clear whether this has anything much to do with the original thing, but if I now define XF to be the proj of this graded ring, then there is a natural morphism of locally ring spaces from XFN to XF. So there is a natural morphism. So I'm taking this graded ring and I'm taking proj in the usual sense to make an ordinary scheme. And then this ordinary scheme has the property that it receives a map like this by, tracing through various ring identifications. YF is, it's this cover of XF. Are you sort of asking where does this map come from? Is that the idea? Or so right, YF is a cover of XFN by the integer, by the group that looks like the integers, which is generated by phi. Okay? Say again? Yeah, well, minus the points where p equals 0 and var pi equals 0. That was YF. So it's the spectrum of AN minus the fixed points of phi. No, as an adic space. Right, remember, right, it was SPA of ANF, but ANF has a non-trivial topology. Yeah, so here I mean as an adic space. So YF is an adic space, so I'm taking the structure sheaf on that adic space. So this thing, so I didn't say this on the board, I said it in my notes, let me just mention it here. You can define, you could write this as B sub an interval where you take not a closed interval, but the whole interval from 0 to 1. Except that you don't do that by, that's not a Banach completion, that's a Frechet completion. So if you take all of the norms on ANF, localized, you can take a Frechet completion where a sequence has to be Cauchy, for each norm individually, but not uniformly. And that, if you do that, that's actually equal to the global sections of this YF, because this YF is a quasi-Stein space. So what I'm doing is I'm really taking the sections of, I'm taking the phi minus p to the n killed sections of this ring, as B01. This can also be written as the phi equals p to the n elements of like B Chris plus. No, the map goes this way. So this is analogous, this is meant to be analogous to what happens in complex algebraic / analytic geometry. So there's an analogy with either complex or there's also rigid analytic gaga, right? So if you have x over c locally of finite type, then you can make an analytification, which is some locally ring space, and there's a natural morphism from here to here, because, right, so for example, let's say x is affine, right, an affine scheme has a universal property, but it's a universal property not just in the category of schemes, but in the category of all locally ring spaces, right? Any morphism, if you have an affine scheme, then any morphism from the coordinate ring to the global sections of some locally ring space gives you a map the other way. And so that gives you this, and right, the Gaga theorem says that, coherent sheaves on here pull back to coherent sheaves on here, and that's an equivalence of categories between coherent sheaves. So the morphism actually does go, the natural morphism in this context is actually going from here to here, because it's sort of using the fact that Yeah, it's using the fact that if you take an affine piece of this, right, an affine piece of this corresponds to, well, you invert some homogeneous thing, and then you take the graded zero ring, well, that will map to all of the rings BI in some natural way, and those maps BI are those maps to the BI are the ones that are defining this natural morphism. So, yes?
So the gamma, those are vector spaces over QP.
Yes, these are vector spaces over QP. I'm not, and they're Banach spaces over QP even, but I don't claim I'm not giving them any extra structure just yet.
How fast is the dimension?
They are, I mean, they're not finite dimensional in the naive sense. They are finite dimensional as what are called Banach-Kolmez spaces. So Banach-Kolmez spaces are, I don't want to try to get into what they are. Those are something like, it's like they're finite dimensional F vector spaces, up to finite dimensional QP vector space modifications. But that doesn't make sense because F is not characteristic zero. But it is, if F is algebraically closed, then it is definitely generated in degree 1. Otherwise, no, I think it's always generated in degree 1. I think so. Yeah, I think it's always generated in degree 1. I mean, this is like writing, I guess the mental model is like you take your favorite curve in normal algebraic geometry and you take your favorite O of 1 and you make the associated graded ring. And then when you take the proj back, you're getting the actual thing you start. Right, or you start with a Riemann surface and then you're getting back the associated curve.
Power series instead of vector.
Yes. Yeah, if I did like power series, yeah, then I'm basically getting back like a P1 basically, if I remember correctly. Like if I did this with a power series ring in 2 variables, yeah, then I'm getting, right, if I did this with like FP double brackets X and Y, then I think I'm just getting back P1 with the homogeneous coordinates X and Y. P1 over the base field. No, not in that context. Yeah, this is formally, it kind of looks like normal graded rings associated to curves, but obviously there's some mysterious thing going on here because these spaces are quite weird. Yes, the line bundle on F is trivial, is trivial as an underlying line bundle with a non-trivial action of phi on it. That's what makes it a non-trivial equivariant line bundle. Oh no, ON is the nth tensor power of O1. Yes, that's easy. I mean, right? I think that's clear from this point of view. Right? E times E goes to E. So yeah, O of n. So these do form a group of vector bundles. Okay. So let's see. We're getting short on time, so I need to find a good place to truncate the discussion here. So let me state the following points, and then we'll leave the rest of the discussion for next time. So first of all, I should tell you that this scheme has good properties. This is a nice scheme. It's connected, separated. It's Noetherian of dimension 1. It's regular. So it's like a smooth curve. But a priori, it's not like a smooth proper curve because, well, how do I express properness? Well, the way I'm going to express properness is in terms of degrees of divisors. So, so for every closed point x of xf, which is of course everything but the generic point because it's connected in Noetherian of dimension 1. So every closed point, the residue field is naturally an untilt of some finite extension of f. basically the point is that the ring A-inf maps to everything in the picture. So you can kind of take this point and then map it to the spectrum of A-inf, and that will give you a primitive ideal. Not necessarily, well, it might not be over F, but after some finite extension of F, it will resolve to some primitive ideal. So this gives me a notion of degree, because I can talk about the degree of this finite extension. So now I can talk about degrees of divisors. So I can say that principal divisors of degree 0 according to this definition. So the degree of every closed point is the degree of the finite extension here. And with that definition, principal divisors have degree 0. I should say out loud that, of course, if F is algebraically closed, then this finite extension has to be trivial, and so all the degrees of closed points are 1. But in general, you get, just like you would in ordinary algebraic geometry, you get points of various extension degrees. And so when you compute the degree of a divisor, you have to put those degrees into the formula. But when you do that, principal divisors have degree 0, and so you can talk about, you have a well-defined notion of the degree of a line bundle. And yeah, so let me state Gaga here, and then we can talk about the classification of vector bundles next time. Was there a question before I? No, let me just. So the form of the Gaga principle that applies in this context is for, first of all, O of 1 is an ample line bundle on XFN, meaning for every coherent sheaf, if you twist by a large enough positive power of O of 1, you get something that's generated by global sections. You also get that the higher cohomology vanishes. There's only, since the thing is one-dimensional, in some sense, you only get H1. H2 and higher are all sort of trivially 0. Is ample, that's not. Okay, and well, if O of 1 is ample, then you can hope for Gaga to be valid, and it is. So pullback of coherent sheaves from XF to XFN, meaning literally pull back along that morphism of locally ring spaces over there, is an equivalence of categories between the coherent sheaves on the two sides, and preserves cohomology. And as usual, when you prove Gaga, you state it in this order, but you prove it in the opposite order. You check preserves cohomology first, and then you use that to prove is an equivalence. Yeah, so this is somehow, the point is that the fact that the principal divisors have degree 0, this is somehow, this is an incarnation of completeness. Maybe I won't say properness, but this is a property of a complete curve that's being imitated in this picture. So this plus this is somehow saying that XF is abstractly like a complete curve. So you have well-defined degrees of line bundles and even vector bundles, and that makes it plausible that you have something like this, and then it turns out to be true. That's right. So on this side, it's really a one-dimensional scheme, so certainly it will vanish past that point. For here, the easiest way to see that is that this thing is covered by two aphanoids. Because remember, what I took my log space, which was this open interval, and I'm wrapping it around itself. So I can, basically, I can cover a circle by two intervals. That's what it comes down to. I can cover a circle with two intervals, and so that covering, when you do check cohomology for that, you only get H1s. So manifestly, everything vanishes above H1 on both sides. This ampleness property implies that when you twist any fixed thing by a large enough power of O of 1, the H1 also drops out in the end. And you just get some H0, which is as I said, it's finite in some weak sense of Banach-Kolmez spaces, but I didn't want to introduce those. So. Okay, yes? So there's a category of coherent sheaves on this on this scheme, and then the pullback is a functor from that category to the category of coherent sheaves on this locally ringed space, and that functor is an equivalence of categories between coherent sheaves on one and coherent sheaves on the other. There's a notion of coherent sheaves on Noetherian adic spaces. Remember, because this thing is built out of principal ideal domains, for a general adic space, this is a point we'll come up with against next time, for a general adic space, it's very hard to do coherent sheaves. Just like on a general scheme that is not locally Noetherian, it's very hard to work with coherent sheaves. So the fact that it makes that I can easily talk about coherent sheaves here is because I have this Noetherian property of the space. Yeah, you could talk about try to talk about finitely presented, or in my work with Liu, I have a notion of pseudo-coherent sheaves, which is like, so pseudo-coherent modules over a ring are ones that emit possibly infinite projective resolutions, but the terms are all finite. Each term is individually finite. So you can talk about sheaves under certain finite generation conditions in more generality, but in this context, everything is Noetherian, so coherent sheaves make sense without any extra song and dance. Okay, so I should stop here for now. So next time, just to tell you my plan is, so we need to talk about the classification of vector bundles. Sorry, I didn't get to that. I think that might actually come up in one of the other lectures. But so next time we'll talk about the classification of vector bundles. I'll just say out loud, it's somehow analogous to the Dione-Manin classification theorem that we saw in Udi's lecture. So we'll talk about the classification of vector bundles on one of these curves, especially when f is algebraically closed. And then I'll say a few words about how you put this construction into a relative framework, because ideally one would like to be able to talk about moduli of vector bundles. But in order to do that, you have to have some notion of relative curves. So tomorrow I'll do two things. I'll talk about the classification of vector bundles, and I'll say a few words very briefly about the relative version of the Farg-Fontaine construction, which was introduced by myself and Liu. No, it's not in the notes. Again, the reference for it is into the book of, well, I gave a reference into the book of Farg-Fontaine, for example. Yeah, my notes do not contain, are missing a lot of proofs of non-trivial things. So mostly they're just references to the relevant literature. Yeah, so I'll mention that next time. So pick 0, in general, I don't know what it is, but if f is algebraically closed, then pick 0 is just the integers. So it'll be just generated by O of 1. But in general, there'll be other stuff in it. But if f is algebraically closed, right? I mean, there's always, I mean, I've given you a map from, I mean, there's obviously a map from Z to pick xf taking n to O of n, and by this property, there's a map going the other way, which makes this the canonical isomorphism. So there's Z plus some extraneous piece, but that extraneous piece will disappear when f is algebraically closed. I don't think it's finitely generated, no. It has to do with the Galois theory of the field F. So it has to do with it has to do with the abelianization of the Galois group of F. When F is algebraically closed, I'll state next time the fact that these are the only line bundles. But in general, there can be, I mean, when I talk about the classification of vector bundles, hopefully that will make it clear why there are extra line bundles when F is not algebraically closed, because there's a representation theoretic reason for them to exist. Yeah. Well, it's characteristic 0 until. So because I inverted P, I'm not going to get the characteristic P untilt of F2 itself. So this is really a story about characteristic 0 untilt. You could, if you wanted to put, you could put 0, you could have worked with this space where you didn't take out the P equals 0. This is actually what you do when you consider moduli spaces of Stukas, like in Schultz's Berkeley notes. He actually has to deal with the analog of this thing where you put the P equals 0 point back in. But in this theory, but that does, right, that's less pretty geometrically because the quotient is no longer a free quotient. So I'm not going to talk about that setup.
Can we hide that one?
Yeah, this thing, again, next time I'll say something about where the excess rank in this comes from. It comes from the abelianization of the Gall group of F.